I think all history of physics shows that at each stage it's difficult to swallow. Think, for instance, Newton, gravitation. It's instantaneous through space. It was extremely difficult for people to accept that. We have been brainwashed since we were kids, and so we accept it.
Hey everyone, thanks for joining us. Today's conversation is in the arena of quantum mechanics, quantum physics. And I'm so pleased that our guest for this conversation is really one of the leading architects of our understanding of quantum mechanics. That's Alain Aspect, Nobel laureate, who is celebrated for a great many achievements. Among them are experiments that confirm quantum entanglement, nonlocality, violations of Bell's inequality. So Alain, thanks so much for joining us today.
My pleasure.
I wanted to actually walk through with you some of the history of quantum mechanics leading up to the groundbreaking work that you and your colleagues have done. But I thought I'd begin with a different question, which is, Albert Einstein went to his grave imagining that there was some deeper theory underlying quantum mechanics that would, in some sense, get rid of all the weirdness if only we could find that theory. Fellow Nobel laureate Gerardo Tuft is, as I understand it, currently working on some ideas in that regard. Where do you stand? Do you think quantum mechanics is it, and we just need to accept the strange picture of reality that you and I will discuss in just a few minutes? Or do you think there might be something to that perspective?
I think that no reasonable physicist thinks that it's frozen forever. But I think that today we have no choice. First, we know that the formalism, the mathematics of quantum mechanics works and allows us to predict the result of any measurement we have tried to do. And second, the question of what kind of image we have in our mind is still open. Either you sit on the side of Niels Bohr and you think that the physical reality is not absolute, that it is contextual, that the image that you get from object depends on the way you observe it, or you sit on the side of Einstein, you think that objects have a physical reality independently of what kind of measuring apparatus you use, but then you have to accept quantum non-locality, that is to say the fact that the physical reality can be influenced at a distance instantaneously. Personally, I sit on the second side, that is to say, I still think of objects with a physical reality, but then I have to accept the idea of non-locality. But once again, I must insist that the results of experiments we do are all predicted correctly by the mathematics of quantum mechanics.
So we'll walk through some of the history of that in just a moment, but can you give a feel, did you go through some kind of intellectual or maybe even emotional upheaval to accept this idea of non-locality?
It was difficult to swallow, but I must say that I have always been influenced by Einstein, because all Einstein's writing are so clear. And then Bell is the same. When you read the paper of Bell, he explained things so clearly that it's natural for me to sit on their side. But of course, the big surprise was that there is something wrong in the full image of Einstein, because to make things a little too simple, but we can say that world vision of Einstein is local realism. That is to say, you have reality, physical reality of objects, and you have locality. And because there is something wrong in that, you can ask yourself the question, what do I abandon? Personally, I abandon locality.
Yeah.
And this was hard to swallow, of course.
Yeah, I mean, it still is, even for us who've just been the beneficiaries of the work and thinking of you and Bell and Einstein and so forth. Let's go back then to the early years of the 20th century, when classical physics had done a remarkably good job, and there were people at the time who thought that classical physics was all there was. Excuse me. I guess it was Max Planck and black body radiation that really began to change our perspective on things. Can you just take us back there with the insights that emerged around 1900?
Well, I think that what you say is not entirely true. Kelvin, the big Kelvin, wrote a paper about the two clouds, and he said these clouds are so dark that we will have to change a lot of things. So sometimes books write that, oh, Kelvin say it's only two clouds. He say it's two dark clouds, very dark clouds. By the way, there is a paper of Pebbles who explained that, but I knew the paper of Kelvin even before I read this paper of Pebbles. And so I think that it is a legend that people did not realize that there was problems, okay, at that time. Then you cite Planck, and you know that Planck did not like at all. He had no choice, but he was desperate. The one who really understood that you have to change is Albert Einstein. It's not Planck who thought seriously. That for Planck, it was a trick, allowing him to render an account of the measurement. But for Einstein, it was a real thing, considering that light is made of particles, least quantum. For Einstein, it was serious. For Planck, it was not so serious. So, you know, well, I have a huge admiration for Einstein, but when you read in detail the history, there is no doubt. It is Einstein, 1905, who realized first all the implication of Planck's discovery that there is a way to make the calculation for black body radiation in cutting the energy in pieces.
And so I guess the reference you're making is Planck needed to introduce the idea, excuse me, of energy in quanta in order for the calculations of black body radiation to work out. But you're right, I've read too, he resisted it as a real quality of the world. It was just sort of a mathematical device. And then Einstein, with the photoelectric effect, really nails this idea that light comes in these little packets, these little bundles called photons.
Yes, and the next big achievement of Einstein regarding light is his famous conference in Salzburg, I think it was 1909, when he say, okay, on the one hand, light, in some cases, I must consider light as made of pieces of least quantum, but on the other hand, he knew the work of Thomas Young and Augustin Fresnel and Maxwell, and he knew that there are many circumstances in which you must consider light as a wave. And Einstein puts explicitly the idea of wave-particle duality for light. And you know, 14 years later, when Louis de Broglie introduced the idea for matter and say, okay, electrons are particles, but they are also waves, and Louis de Broglie was explicitly influenced by the conference of Einstein 1909.
And I gather the history as well is that when de Broglie wrote that in his PhD thesis, people didn't really know what to make of it. And they called in Einstein to give his opinion.
Yes.
And ultimately they gave the nod of approval.
Yes, he is well known. Langevin, you know, Langevin got a Nobel Prize also, but Langevin was in the thesis committee of Einstein, of de Broglie, asked Einstein the opinion, and Einstein say, yes, he has shown us a part of the big mystery or something like that. I don't remember the exact words.
So by the mid-1920s, it's clear that there is this unexpected duality between particles and waves, both for light and for matter. But there was still a question of what the waves actually meant. And then it really wasn't until Max Born, I guess, in 1926 or so, that this idea of probability finds its way into physics. And in your view, was this sort of the critical moment when our view of reality really begins to change?
Probably yes, because for instance, from what I read, until that moment, Schrödinger really thought of the waves as some kind of real waves. And of course, after Max Born interpretation, it became a problem. And I think that the problem has not been solved. It still depends on the point of view. Still nowadays, most of my colleagues, I think, believe that the wave function is not a real thing. I tend to think of it as the physical reality. But I am a minority.
I tend to, I have the same opinion, but a question that then immediately comes to mind is, if you're dealing with a single particle, its wave function, at least non-relativistic wave function, exists in three-dimensional space, given the probability of the particle at one location or another. When you have two particles, now you've got 6 coordinates, 3 coordinates for each particle. The wave function lives in 6 dimensions. With n particles, it lives in 3n dimensions. So if you think of it as a real physical thing, do you imagine that 3n dimensional space is a part of some description of reality?
No. There, I think that when I have an object which is localized in space-time, for instance, with 2 entangled particles, but there is no, take the experiment that we did with photon. The photon is localized in space-time. It's a wave packet of a few nanosecond length, so it's here in space-time. And so I think of the physical reality of that photon, being influenced by what happens on the other side. But, it's just a hand-waving picture. Once again, there is no problem in the calculation. I know how to do the calculation. So the way I use these images, which I must admit are not very consistent, but it doesn't matter. It guides my intuition. And then I say, if I do that, maybe I will observe this or that. And then I write equations on the paper and I look if the equations support my intuition. So right. I'm not a philosopher. I don't pretend that I have a consistent image, but I claim that I have a useful image. It's useful for me for guiding my intuition.
Does that ever trouble you, that it's hard for us to put forward a fully consistent picture of the external world when we face these quantum conundrums?
Well, I think all history of physics shows that at each stage it's difficult to swallow. Think, for instance, of universal gravitation, of Newton, gravitation. It's instantaneous through space. It was extremely difficult for people to accept that, And there is no contact, and it's instantaneous. But we have been brainwashed since we were kids, and so we accept it. But if you think of it, it's as difficult to accept. Now think of Maxwell and his difficulty with the electromagnetic field in the vacuum. So for Maxwell, there were plenty, a full ether and everything below, and we have been brainwashed by our professor who tell us that the electric field and the magnetic field travel in space. So I think that it's all the history of physics that there are things which are shocking, but we get used to it. And at the end of the day, the only important thing is, can I calculate what will happen in this situation? And once the calculation is done, does nature follow what I have calculated? The answer is yes. Then I have a good theory, and then it's my own personal business to develop an image in my mind.
And so would you say that view is reminiscent of Niels Bohr?
No, because Niels Bohr tried to be serious philosopher. But then, although he claimed he was a realist, his physical reality is not palatable for me. Because a physical reality which depends, which is contextual, which depends on the kind of tool I use to observe this reality, for me is not a physical reality. So, no, I certainly sit on the side of Einstein. I think that objects have a physical reality.
And so if we then dig in a little bit more deeply into some of the puzzles of quantum mechanics, the famous of all experiments is the double slit experiment that I think many in our audience have seen. There's an interesting variant on that experiment, the Mach-Zehnder interferometer.
Yes.
Which we'll show a picture of to our audience so that they know what we're referring to. You know, it's a famous example where you fire light at a beam splitter. If you can get it down to individual photons, which you and your colleagues were the first to ever be able to do.
It was a PhD thesis of my first PhD student, Philippe Grangier, and we were the first to produce one photon separated from the next one. One photon after one photon. That was a real achievement. Nobody before us had been able to produce a single photon isolated from the next one.
Which is a critical step forward and really pushes our understanding to the limit, because an individual photon can't split in two.
Yeah.
If it encounters a splitter, it either goes, say, left or it goes right. Waves, of course, can split going left and right. And so can you take us through some of the puzzles in this experiment that the individual photon really presents you with?
Well, I think that at the end, the only thing I can do is once again invoke non-locality. That is to say, I think of the single photon wave packet as being split on the beam splitter. So now I have half a wave packet on the right and half of the wave packet on the left. But if I measure on the right, if I detect the photon on the right, instantaneously the other wave packet collapses to zero. So once again, my image is non-local image.
And so you would say then, in some sense, the photon is traveling both, or would you say it's not a well-defined question?
No, I would say it's traveling both sides. But if I try to ask the question, are you on this side? Either it answers yes or no, but the answer will be only about one side.
And so that invokes the famous quantum measurement problem. You undertake a measurement and it impacts the wave function, the probability wave for the system. Do you have in your mind an intuition about the way that this measurement process causes that?
No idea. I think it's really one of the big mysteries or the big problems of quantum mechanics, because I can tell you that if I detect the single photon, I use an apparatus, for instance, a photomultiplier or a detector, which has some kind of irreversible process in it. So you can invoke that. But it's just hand waving, because nobody has a real detailed description of what happens in the photomultiplier. And moreover, there is a fundamental difficulty, for instance, for cosmologists. Because when you have a cosmologist, he thinks of the wave function of the whole universe, and then there is no measuring apparatus to measure the whole universe. So I think it's really an open question.
And so do you have any feeling about, say, the many worlds approach that Hugh Everett introduced in the 50s?
I know that many cosmologists consider seriously the many worlds universe as a solution to their problem. My point of view is that it is a logical solution, but it's absolutely not palatable. And so in what I am doing, that is to say, I have a measuring apparatus, I don't need the many universe interpretation, and it's hard for me I'm certainly not convinced by the many world interpretation, but I can understand as a cosmologist do not know what to do except that.
And how about, for instance, the approach that was introduced some years ago about spontaneous collapse, changing Schrodinger's equation to have new terms that cause the wave function to undergo the collapse that you were referring to?
Well, many people have been considering this, and nobody could come with something convincing, but I think that it is an interesting choice, yes.
And so, given that we don't have a solution to the quantum measurement problem, does that give you a feeling that quantum mechanics is very much a work in progress, or that it's unstable, or that it's just a rule of thumb that allows us to make these incredibly detailed predictions, but it's not really the full thing? It's not really the mind of God, as Einstein would describe it?
Well, certainly the dream of Einstein is not close to us, but I think that quantum mechanics is certainly extremely consistent, provided that you accept the postulate that when you do a measurement, there is a collapse of the wave function. Once again, some kind of non-local event. But you have the same kind of problem in classical physics with the second principle of thermodynamics. You have to admit it. There are so-called demonstrations of the second principle of thermodynamics, for instance, the H theorem of Boltzmann. But at the end of the day, to do this demonstration, you must accept something. There is no rigorous demonstration of the second principle of thermodynamics that you could derive from the fundamental laws of mechanics. And, we anyway think that the second principle of thermodynamics is extremely solid and serious. And I think that we have a similar situation with quantum mechanics. We have no sign that it does not work somewhere, which is a pity, because any reasonable physicist thinks that at one point we should find a broader theory. But nobody has any idea of where it would be.
Yeah, it's almost been unreasonably accurate and unreasonably effective.
Yes. And unreasonably resisting all attacks.
Yes, exactly. Now, one attack historically took place in 1935 when Einstein and his two colleagues, Boris Podolsky and Nathan Rosen, wrote one of the most famous of all papers in physics.
Yeah, sure.
And it has to do with the non-locality that you've made reference to.
Exactly.
We've seen sort of hints. We've sort of seen hints of non-locality in what you described. Can you just take us through a brief overview of that famous EPR paper?
Yes, and before doing that, I should emphasize that there should be no confusion between the discussion of 1927 in the Solvay meeting, in a Solvay conference, because in 1927 it was about a single particle. And Einstein tried to design a Gedanken experiment, a thought experiment, in which he could measure both velocity and position better than allowed by the formalism, and so he concluded that the formalism was not complete. But for each attack of Einstein, Bohr could reply in a scientific way. That is to say, there is a mistake in your reasoning at this point. You forgot that the slit on a spring is a quantum object, and if you take into account the fact that it is a quantum object, your reasoning is incorrect. In 1935, it was totally, it was my subject. In 1935, it was different. It was about two particles, and the reasoning of Einstein is very convincing, and the reply of Bohr is not a scientific reply. It's not a reply saying you made a mistake in your reasoning. He said your notion of physical reality is not correct. So it becomes an epistemological debate. Bohr has a certain point of view on the physical reality, and Einstein has another point of view of the physical reality. So the reply of Bohr is totally different in nature. It's no longer a demonstration that there is a mistake in the reasoning. It's difference in philosophy, in epistemology. And this is why, until John Bell, it was possible, and probably it was a point of view of Einstein, to believe that you can complete quantum mechanics and still have no problem with the formalism of quantum mechanics. And it's only after John Bell that we know that if we want to complete quantum mechanics following the point of view of Einstein, then there is a problem, and we have to abandon something in the point of view of Einstein.
Now, you mentioned Bohr's response to the EPR paper, this famous paper that said that, either there's some sort of spooky connection that Einstein didn't believe between distant particles, or they had definite features, hidden variables, as we call them, even though quantum mechanics couldn't access them. I've tried to read Bohr's response to those papers.
And
it's very hard to make heads or tails of what it is that he's saying.
Exactly. It's exactly what I was telling you. In contrast to the replies of 1927, which were as clear as Bohr can be, in 35, as you say, either you believe in Bohr's philosophy and then you are convinced, but if a priori you are not convinced by Bohr philosophies, you have no reason to follow him.
Yeah. Now, there was a lot of activity in 1935, 1936 in response to the EPR paper, but it kind of died out pretty quickly until some decades later.
Until John Bell.
Was that because... Until John Bell. And I presume that was because most people thought it was just, philosophy or metaphysics. It wasn't something that you could actually measure.
Exactly. I think that what you say is exactly what happened. Quantum mechanics was working very well for describing what happens in the laboratory. And on the other hand, there was no debate about the way to do the calculation. It's only a question of epistemology, of philosophy. And so people thought that it was more urgent to use quantum mechanics to describe the world than to think about the foundations.
Yeah, I think that's what the historical record shows pretty clearly.
Yes.
And then, but there were some thinkers who were willing to press on with these ideas. And of course, John Bell was the most successful of all of them. And so he starts to think about these ideas, I guess, in the late 50s and then in the early 60s, and comes to a conclusion that was pretty unexpected.
Yes. The exact history is the following. In the 50s, David Bohm designed a theory with hidden variables along the ideas of Einstein, okay? And on the other hand, in the famous book of von Neumann, there was a proof that you cannot complete quantum mechanics. But there is this theory of Bohm, which shows that there is something wrong in the proof of von Neumann. And Bell is the one who finds a mistake in von Neumann. There are not many people who found a mistake in von Neumann. And so Bell found the mistake in von Neumann, but while working so hard for understanding where is the mistake in von Neumann, Bell realized that if you impose a locality condition, then you have a problem, and you cannot have a local hidden variable theory rendering an account of all the prediction of quantum mechanics in the Einstein-Podolsky-Rosen situation. But we must give credit to Bohm in two senses. First, he had designed his theory. And second, it's Bohm who redesigned the EPR reasoning not with position and velocity, which are continuous variables. It redesigned it with dichotomic variable, spin 1/2. When you do a measurement, you get either up or down, only two possible results. And this is the key for testing Bell's inequality. Bell's inequality applied to dichotomic observable, spin 1/2 component, polarization component, etc. So Bohm deserves a lot of credit. But to finish the story, what Bell realized is that for a single particle, the Bohm theory is okay, but when you have two particles in an entangled state, the Bohm theory is non-local. And then the loop is closed.
Yes. No, it's an important historical point. You know, David Bohm isn't as well known as he probably should be. You know, I think famously among physicists, he went up against the House Committee on Un-American Activities in the
Absolutely.
1950s and invoked the Fifth Amendment repeatedly, which I gather in those days was viewed as some kind of admission of guilt, and got dismissed from Princeton and had to go to Brazil and to Israel, ultimately to London. But you're absolutely right. It was his work, which was, I believe, resurrecting in some sense, even though he didn't know it, de Broglie's work. In the 1920s, de Broglie had his own version of this particular approach to quantum mechanics,
Yes.
Which ultimately, as you say, inspired Bell to try to come up with a version of a hidden variables theory that wouldn't have this non-locality, and winds up proving a theorem that if a certain measurement of these, in the diatomic example, exceeds a certain value, then you will be unable to complete quantum mechanics in this local hidden variables approach. So people begin to test this, but perhaps it's also worth noting, Bell published this result in a very strange, obscure journal, which I don't think lasted very long, which
Yes.
in part is why it didn't get the attention initially that it deserved. How did you come upon the Bell paper?
Oh, it's because Abner Shimoni, who was interested in this issue, was invited in the University of Orsay by Bernard Espagna, who was also interested in the subject. And it was in 72 or 73, and there was already the experiment of Clauser and Freedman, who had given a result in favor of quantum mechanics and against local hidden variable. But at the same time, there was an experiment in Harvard with the opposite result. And then Shimoni comes to Orsay and say, look, there is this problem. Don't you have an experimentalist here who would be happy to work on that? And they gave it. I was not in Orsay at that time. I was in Africa for my military, okay, as a professor, as a teacher in Africa. But they gave it to a young professor in Institut Optique who had been involved in experiment of interference with weak light, etc., another debate. And when I came back and visited his professor and say, would you have a subject interesting, something in the spirit of what you did with weak light, single photon interference? He handed me a file, and the first paper on the file was John Bell's paper. It's a 4-page or 5-page paper. I read it, and after 2 hours, I knew that I wanted to work on that. I mean, I fell in love. It was love at first sight, as Nicolas Gisin says, when I saw that. I knew I wanted to work on that. And then, of course, the experiment of Clauser and Freedman. And so I had to find an idea for doing something different. And after thinking for some time, I came to the idea that I wanted to switch the orientation of the polarizers while the photons were in flight. But this paper,
But can you give us more detail on that point? Because that's an important point, which I guess Bell does make reference to in the paper obliquely.
Of course. In the conclusion of his paper, Bell say there is a way out of my conclusion would be the fact that there is some kind of interaction between the two sides of the experiment, because if the apparatus are held fixed, they have all time necessary to exchange some kind of information, of interaction, and reach an equilibrium. And so Bell says it would be interesting, as suggested once again by Bohm and Aronoff in a paper of 57, I think, it would be interesting to change the orientation of the measuring apparatus while the photons are in flight so that the other, on the other side, cannot know, between quotes, cannot be informed of the orientation of the first one. And when I read that, I say, this is what I want to know. And by the way, since you are interested in history, the paper of Bohm and Aronoff in 57 is extremely interesting because they realized that the gamma photons, which are emitted in disintegration of positronium, these gamma photons are entangled. But they also realize that there is no data available to know more. And one very interesting point about history of science is that in 54, Madame Wu, the great Madame Wu, the one who found parity violation, she does an experiment about the correlation between the photons that she gets in disintegration of positronium. And in her paper, there is absolutely no reference to EPR. Once again, it's Bohm. It's Bohm who understands that this experiment has a relation to EPR.
Wow. I didn't know that history at all. I don't know the 57 paper. I'm going to have to look that up.
Oh, yes.
That's fascinating.
It's cited. It's cited in our paper. It's cited in Bell paper and cited by me also.
Huh. Amazing. And so then the goal was to do a version of this EPR using polarization, using spins.
Yes.
But have the two detectors sufficiently far apart and sufficiently fast switching that no signal could possibly go between them.
Yes, I did.
How challenging was it to create that setup?
Yes, it was challenging, but I got an idea. The idea was to use the interaction between light and a standing acoustic wave. And so I was using diffraction on a standing acoustic wave. And when you have a standing wave, either the wave is on, you have a full modulation, and then a quarter of period later, there is no more wave. Everything is flat if you think of the string, a string of a guitar. And then a quarter of period later, again, So when you have diffraction, it's diffracted in one direction. When there is no diffraction, light goes through. And there is a regime called the Bragg regime, where when you have the maximum of diffraction, it's 100% of the light which is redirected on the side. And so I built a system like that, and it worked.
And did it work immediately? I mean, how was it a lot of trial and error?
It took me 7 years to develop the experiment. But the biggest work was to build a source of entangled photon much more efficient than the one of Clauser or the one of Holt and Pipkin. I could benefit from the invention or discovery, you name it, of two-photon absorption, which allowed me to excite selectively, precisely the upper level of calcium from which the calcium atom has no choice. The calcium atom can only deliver a pair of entangled photons. While in the case of my colleagues 10 years earlier, sometimes they would have the right pair, and quite often they would have other kinds of photons. So this use of two lasers to selectively excite the upper level of calcium was crucial. And so my source was orders of magnitude better. It took me 5 years to develop it. And then I could build the various devices to do the measurements.
Now, John Bell's view was, his intuition was that Einstein was going to be right, that quantum mechanics was going to be shown slightly wrong in these circumstances. Did you have that intuition too? Were you surprised at your own results?
No. I was both convinced that Einstein was right, but that quantum mechanics should be right. So it was conflict. I was schizophrenic. And so this is why I wanted to do the experiment, to settle the question. I was convinced by both sides, okay? And so I wanted to settle the debate. But, from the first day when I started this program, I visited John Bell to get his opinion about is it interesting or not, and he told me that it was interesting, and so I kept him informed, and he never had doubts about the experiment. He respected a lot the experiment, and when I told him this is the result I had, he said, I am sorry, but I believe the result of your experiment. He was in my thesis committee. And he declared it publicly. He said, I am sorry of the result of Alain, but I must respect it.
Wow, that's amazing. Now, there are people who talk about potential loopholes even today in the result. Do you consider any of them serious?
No, come on. In my experiment, of course, there were several loopholes. People have addressed them, and now all the loopholes have been closed one after the other one. Okay, so I think that, no, there is no debate. In my opinion, of course, say, okay, you have this, you have that, okay, but there is strong evidence that, it works as predicted by quantum mechanics, period.
And so you've already given your views on the many worlds approach, but many worlders will make an argument that the non-locality is not required if you allow the many worlds approach to the quantum measurement problem. But I gather you'll say you're just not interested in that approach to the quantum measurement.
I think that accepting the many world approach is worse than accepting non-locality.
Yeah, sure. No, I feel similarly on that front. What about people who make reference to something that seems maybe ridiculous at some level, but they talk about free will? Right? Do you actually have the freedom to make the choices that you think that you do, which are necessary for the data to yield this result?
My answer is simple. If I don't have free will to tune the knob of my apparatus, I stop being a physicist and I do something else. I believe that the work of an experimental physicist is based on the idea that I am free of the setting of the knobs I am using. Okay, so for me, there is no... But I understand, logically they can... But, it seems to me totally uninteresting. Because any result that I have in front of me, I can say, this was written in the great book from the first day of the universe, at the Big Bang. So it's an explanation for everything, to invoke something in the past. So, it's not the kind of physics I want to do.
Now, when people talk about non-locality and quantum mechanics and, for instance, special relativity, usually the argument is made that the non-locality is not usable to send information from place to place at fashion the speed of light. Does that satisfy you? Is that enough to have full compatibility with special relativity?
I think so. I think that Einstein did not know that, but Einstein's causality, we have to restrict it to what people call signaling. That is to say, sending a real useful signal from here to there. And the fact that we can demonstrate that even with EPR, non-locality, etc., you cannot signal, you cannot send a useful signal faster than light, I think that it allows us to feel not too much uncomfortable. You should realize that the impossibility to send a useful signal faster than light is related to the random character of quantum physics. When I receive a photon, I do a measurement of polarization. It can be either plus or minus, okay? If I could force it to go to plus, then I could send a message faster than light. But I have no choice. I have just to let the photon do what it wants to do. And so this fundamental randomness of quantum mechanics is also involved in the reasoning showing that you cannot send a useful message faster than light.
Yeah, absolutely. And in terms of the utility of this non-locality, of course, people have leveraged it for things like quantum teleportation. Your fellow Nobel laureate Anton Zeilinger, of course, famously is among the physicists who do that. Where do you see this non-locality going in the future? Of course, quantum computers is a domain, quantum teleportation. Where does this lead us, do you think?
In the future, I don't know, but I can tell you that for me, non-locality is very useful because if you think, for instance, of the quantum cryptography scheme of Arthur Eckert, for instance, using the idea of non-locality, I can immediately understand why it is secure. It's secure because non-locality amounts to saying that the two photons progress, okay, and until the last moment, it can be as well plus as minus, okay? And non-locality says if it is plus here, immediately it's plus on the other side. And if it is minus, immediately it's minus on the other side. But then, if you follow me, it means that in between, there is nothing to spy. So the eavesdropper who is here has nothing to observe. And so the image of non-locality allows me to understand immediately while the Eckert scheme is a good scheme. And you mentioned quantum teleportation, which is teleporting the quantum state of one object onto another object. Here again, just by thinking of non-locality, it allows me to emphasize that you need a quantum memory here to put the second photon on hold while there is a classical signal coming by a classical channel and it takes some time. So you have two channels, the quantum channel, which is instantaneous, something happened, but then you can keep that photon until the classical signal comes. And once again, for me, non-locality is good for my intuition. And at the end, I will do the calculation as everybody. But I have images which allow me to understand instantaneously, so to speak, immediately, why it works and why it is interesting.
So would you say that, you mentioned earlier how we get used to things in physics that may have disturbed us when we first learned about them, but by brute familiarity, we just encounter it over and over again and we get used to it and we absorb it. Would you describe that as your journey with entanglement and non-locality?
Yes, definitely. And you know, there is a fantastic interview of John Bell, where John Bell say, "I am a realist." So I encourage you look into on internet, and you will find it. And so what Bell says, and I think he's perfectly right, he say, in fact, everybody is realist. But people don't want to admit it. People who sit on the side of the Copenhagen interpretation pretend that they are not realist. But Bell says much better than I'm telling you now. He says, I am a realist, but in fact, every physicist when he is in his lab is a realist. And I think it goes to what you say, because if you are a realist, at the end, you have to accept some kind of non-locality. Or you belong to the school of shut up and calculate, and you say, I do the calculation, and I don't want to have any image, period. But if you have an image, the image is about physical reality, and if you have an image about physical reality, it seems to me difficult to avoid non-locality.
And have you followed some of the work in the last 10 years or so relating potentially EPR to ER, the Einstein-Rosen paper of 1935 to do with wormholes?
No, I don't know about that. It's
okay.
beyond my understanding of theoretical physics.
Sure. And so do you think we should continue to search for better pictures of non-locality, something that gives us some kind of sense of how two things that are far apart can somehow be connected? Or should we just absorb it as part of the way the world works and go forward?
I think everybody has to decide what is his or her priority. Okay, personally, I built my image only by practicing, doing calculation, going to the lab, bringing images or building images in my mind, and I tried to read paper by philosopher. It did not help me. So I never tried to do it systematically. But if somebody wants to focus on it and spend all his or her time on that, I have no objection. It was not my approach. My approach was to do physics, try to develop images, and build my own picture, which I admit is probably inconsistent, but for me it's useful.
And so what are you working on now?
You know, I am an old man. I'm retired, and my main job is to use the popularity of the Nobel Prize to speak to the general public. I think I have no need to tell you. You see that in your own country. There are so many attacks against science that I use the fact that I can speak on the radio, on the TV, give conferences, go to high school, etc., to speak in favor of science. I'm no longer doing research myself, but I keep myself much informed about the progress of quantum technologies, in particular quantum computer, because I happen to be one of a co-founder of a startup, which is very good. And so I follow the progress of quantum computing, etc., but I am not involved myself in the detail of research. It's too demanding, and I use my time in speaking to the general public.
Well, it's well-deserved, and that's an important undertaking. Where do you think we stand with quantum computing?
Well, in the middle. We don't know if we will have a quantum computer as wonderful as we dream of, but we have already interesting results. In quantum simulation, my colleague and former student Antoine Broes has here in Institut d'Optique a quantum computer with neutral atoms which can solve the Ising problem with 300 particles. You cannot solve the problem with a classical computer, that problem with a classical computer. So we have already some evidence that we can do something with a quantum computer. Will we have a perfect quantum computer, error corrected, etc.? Nobody knows. And I think that it is a fantastic, extremely interesting research for the following reason. You know that we don't know if there is a limit between the quantum world and the macroscopic world. And a quantum computer is trying to have more and more quantum bits entangled together. Let's suppose that we find that there is a limit. It would be a fantastic discovery. Or the difficulty is only technological, and we will have a good quantum computer at some point.
Is your intuition that there will not be a limit?
I think we will have very good quantum computers, but once again, nobody knows. Don't believe me. I think, but there are people who think that we will not have, and it's just a matter. I am an optimistic person.
One final question. You made reference to the state of the world right now, which, without getting into details, is very troubling for scientists around the world, especially in the United States. Do you maintain your optimism in spite of the situation?
Yes. First, in Europe, up to now, we still have a decent support to science, although, of course, we have people who don't believe in science in Europe, but at least we don't have a health minister who tell us that vaccination is not good. Okay, we are in the country of Pasteur, and we still believe that vaccination is useful. And the United States, I'm an optimistic in the sense that I'm ready to believe that your constitution is robust enough that at the end, reason will win.
Well, thank you so much for joining us, Alain Aspect, and giving us insight into the weird, wonderful world of quantum mechanics, and best of luck to you going forward.
I am, again, an optimist, and I think that the good science will always interest many people.
Let's hope you're right. I'm with you. Thanks so much.
Bye-bye.